Okay, what I want to do in this segment is we want to review the concept of transformations, but like I said, there are DVDs available on the other material back in the algebra DVDs that you might want to go back and watch. So I want to spend some time on this. Let's see, I wanted to make another comment about these things. Both the sine and cosine functions are oftentimes called sinusoids. It's a fancy word. Sinusoids. And in the real world applications like springs, bobbing up and down with a mass attached to them, those kind of things, they're also called harmonic models. Harmonic models. And some of you are musicians, or most of us appreciate music. That is a mixture of waves that are sinusoids. Particular tones that we hear are particular sinusoids with a certain frequency. And we've all heard those words before, and we're actually going to learn what they mean and how you mathematically describe those kind of things. Okay, frequency, period, that type of thing. Very, very important. Okay, and also harmonic models. Okay, let's review transformations, but I'm not going to do it from the ground zero up. I'm going to give you a very quick summary of transformations that you've done from algebra, and I'm going to probably show it in a little more sophisticated way than the way you've seen it before. So let me grab my markers. As you progress through applying mathematics or moving on in mathematics courses, we keep recycling back onto earlier material because we all know that we forget this stuff if we don't keep the repetition going. So we always are going back. I like to think of it like a big soup pot, soup kettle, and we keep stirring the pot, coming back to those same ingredients that are in there, but then we keep adding new things into the pot, okay, until we have a giant stew. Okay, and we're very confused frequently when we put new ingredients in. But it takes a little practice, sampling all that stuff to get good at it. Okay, we are very familiar with this. The input is clearly X, and the output is clearly Y. Okay, and to use this kind of notation, a graphical representation of these things must pass a vertical line test to use this notation. This is very particular. This kind of a recipe structure is very particular if you use this kind of math notation. Here's what I want us to look at. You're going to love this one. A f of bx minus c plus k. Where A, B, C, and K are all numbers, constants. A, B, C, and K are constants. The independent variable is X. The dependent variable is after you put a value in for the independent variable and you calculate this result, the y value depends upon what x is. The y value, the output, depends upon what the input is. So the dependent variable is y. Very familiar territory. Notice the fundamental recipe is right here, right? This is the process that you are going to apply to the independent variable. You're going to take the input, you're going to multiply it by some constant, subtract possibly something from it, and you get a new input to the recipe. And then you're going to multiply that result times a, and then finally you have all of this, you then are going to add k to it. What's important to remember is that a and k are outside of the input portion. The a and the k are separate from f. Feel good? Algebraically, can't we move a and k over to the other side of the equation and tie it on to y through algebra processes? Okay? And I think you all know that k simply does what to the function? Be careful. Are you going this way? Or are you adding something up or down to it? Isn't this stuff here a result? Isn't this an output? Well, if you compute this thing, isn't this a part of the output? Isn't this a part of the output? And then aren't you adding, or if that's negative, subtracting something from the output? And on your graph, that is either lifting up if it's positive or taking it down negative, right? So the k is a vertical shift. That should be real comfortable to you. It's not, that k is not a horizontal shift. It's not doing this. It is doing something like this to it. Okay. So what I'm going to do is algebraically subtract k from both sides, move it over here, and then divide both sides by a. And what we're going to get is this. And that's equal to this. Now go back to your algebra background thinking for a second. We talked a moment ago about what k is. What is a? What does a do to the original, this is called our old or our elementary function? The old or the elementary function up here. So what does the a out in front of that do? Okay. What variable are you messing with? Are you messing with the input or are you messing with the output? You're multiplying the output, aren't you? Isn't this the output? Aren't you multiplying the output times something? What does that do? I'm seeing people do this. You are multiplying the output. On a graph, the output are the y readings. You're multiplying those by some value. Now, you folks are experts at something like this. Right? You've got that fundamental graph in your head, x squared. This thing is 100 times, on the graph, 100 times as tall, isn't it? This thing is x squared tall, and so you're multiplying those y readings there, those outputs, by 100, and you're going to get a tall, skinny-looking parabola for this thing. You're good at that. Do you see where we're going with this? We can just take those sine or cosine, nice cycling functions, and we can multiply them by something out in front. Like, what if I multiplied them by 110? Does that number kind of ring a bell? As I said earlier, you ever stuck your finger or a screwdriver in a light socket? Don't do that. You learned that as a little kid, right? Okay. You got alternating current, rising to voltage values up near 110 or so, and dropping to negative, oscillating back and forth very quickly. Okay, alternating. So you can amplify a sinusoid. You can stretch or squeeze it vertically by a multiplier out in front of the function. Notice it's part of the y value. That's why I moved it over here. That's why I moved it over here. So if A was less than 0, what if this was a negative 100, folks? If that was a negative 100? What would that graph look like? It's upside down, tall, and skinny, isn't it? You can, in a split second, you should be able to draw that. Split second. So you know clearly, you can see the range, negative infinity up to 0. You're good, should be good with that. Okay. We can do the same thing over here. If we put a negative in general on this, then that's going to turn whatever the fundamental function was, it's going to turn it upside down. So if A is less than 0, it's going to turn the graph upside down. If that value of A, let's say I take the absolute of it, is greater than 0, 1, like 2, 3, 100, 1,000, if the absolute value of that number here is bigger than 1, it's going to do what to the graph? Bigger than 1, it's going to stretch it vertically. It's going to stretch the graph vertically. We are going to amplify. We are going to amplify the sinusoid. You all own amplifiers. You all have volume controls on your stereos or your iPods or your cell phones. You have volume controls. You're amplifying the signal or diminishing it. That's vocabulary we use in applying trigonometry. So you can amplify a signal by putting a multiplier on your sinusoid of some number bigger than 1. What if the number was a half out in front right here? Yeah, it's going to make it half as tall, isn't it? Half as tall. So if the absolute value of that coefficient is less than 1, things like a half, a third, a tenth, a millionth, it's going to act as a vertical compression or a squeeze on the graph. And we already talked about the K. The K is a vertical shift, up or down. K is a vertical shift. Okay. I'm not going to get to a third segment today, but what I'm going to do is I am talking about graphing with transforms. Right? Aren't we talking about that? We're talking about vertically stretching, squeezing, maybe turning the darn thing upside down. Couldn't we take that sine or the cosine and turn them upside down real easily by just slapping a negative out in front on the coefficient? Yeah, out in front of the function. Okay. I like to call this cluster right here the y stuff. You won't see a textbook say that, okay? But I like to call that the y stuff. It's the output. It's the output information. It relates, this is the new y, isn't it? Isn't this a new y reading here? If you took some graph and you maybe added 30 to it, or say y minus 30 here, that'd be the same as a plus 30 there. A minus 30 here, y minus 30 would be a plus 30 there. That would just shift the graph up 30. And if I put something like 100 here, that would first of all stretch it and make it 100 times as tall, and then I would lift it up 30. Okay? So then this is a new y reading, isn't it? A new y reading associated with those transformations. So this is the y, new y. Back up here, this is the old y. So aren't we taking this old y and replacing it with all of this? Okay. With that in mind, this old y, the old y is equal to this new y minus k over a. And like I said a few minutes ago, I'm showing you this transformation information in a different way than you saw it back in algebra. It's the same stuff you did, but I'm just showing it to you in a little more sophisticated fashion. There's a reason I'm doing this, and you'll see that in a second. Now look at what the new y reading is going to be. The new y reading, when you do your algebra here, multiplying both sides by a, that's going to kick this a up over here as a multiplier. And then I'm going to move the k over by adding k to both sides. So I'm going to get a times the old y plus k. I think you can look at this and see clearly that you're taking your old y readings from your original elementary function, you're multiplying them by, think of the order of operations. You're multiplying those old y readings on your graph or in a table of values. You're multiplying those old y readings by some number, and then finally you're adding k to it. Okay. Should be familiar territory, just presented in a little more sophisticated fashion. Why did I do that? Just to make things more sophisticated? No. Does it make sense to you? You didn't have to do this in algebra, but we do have to do it in trigonometry. Doesn't it make sense to you that we want to take these things like the sine and cosine and be able to stretch or squeeze them to make them maybe finish a cycle in maybe a certain amount of time? And maybe we want to not only just stretch and squeeze them, but then shift them horizontally, right or left. Okay? Very important. And what I'm trying to show you is the fact that the behavior, the algebraic behavior, is identical in here to what you see right here. But this doesn't look like this structure, does it? This doesn't look like this old x, right? Isn't this your old x right in here? That transform to get this thing doesn't look the same, does it? So let's see what's going on here. Let's look at this x, old x, and see how it relates to this new x here. So the old x now is going to be equal to b times some new x minus c. Let's solve this for the new x. The new x naught plus c over b. If I do the algebra here, right? Adding c to both sides, move this down under there. Okay. And I want to show you something in here. So watch this. If I take this structure and I factor out b, I have bx here. The problem is I don't have a b tied in here with c, do I? But what I'm going to do, I'm going to fool it by doing this. Can't I do that algebraically? Introduce a factor b here and here, which essentially is just a multiplier of 1 on c. And if I grab a hold of this b right here and factor it inside there, that's going to take us to this. Just a little bit of algebra here. I'm just factoring this common factor in the numerator out, b. There it is. And what I'm going to do now is take that b out in front, that coefficient, and I'm going to move it down underneath this. Remember invert and multiply? So if I take that b down underneath, it doesn't go down there just as b. It goes down as 1 over b underneath there. So this becomes f of x minus c over b divided by 1 over b. This may be confusing at this point to everybody. Probably is. But what I want you to observe is look at this structure here. There's something you're familiar with here. This is the vertical stuff, the Y stuff. The vertical shift after you have stretched or squeezed a graph or turned it upside down, A. And look at the X stuff over there on the right side. This is your horizontal shift to the right or to the left, right here. And this 1 over B factor is analogous to this thing called A over here. This is the thing that will cause the graph to get shifted, flipped around a y-axis, possibly, or stretched or squeezed horizontally, like that. And just so that you don't feel totally baffled by that, what I would like you to observe, to tie this to what we've done today, is what if I had something like this? Y equals the sine of 2 theta. Take it back to something not as complex as what you're seeing down here. If I would rewrite that, isn't that the same algebraically as the sine of theta over 1/2? Isn't this the same as this? Okay. And if you would kick this into your calculator, what you are going to see is you are going to see a nice looking sine graph here. But this is not 360 anymore, folks. That's a 2, right? That's a 2, which is analogous to this being 1/2, which means the graph has been squeezed in from its original elementary form, and this is 180 degrees instead of 360. So it'll finish 2 cycles in 360 degrees instead of the usual 180. So that factor that's underneath there makes the graph half as wide. But here's how you oftentimes get confused. You'll see this 2 sitting here, and you might think it's what's happened. You might think it's been stretched out and take 720 degrees to finish its cycle. Instead, it's actually half as wide instead of twice as wide. Okay, I expect everybody to be relatively confused at this point, okay? So in Thursday's session, we'll practice over and over again these kind of applications, okay? So that's it for today.